And let me give you the outline for today's lesson. So in today's lesson, what we are going to do is we are going to look at first the performance specifications. There are two ways to meet these performance specifications. One is using the time domain, and what this time domain means is you have a system. Either you excite the system with a constant input, you excite the system with a sinusoidal input, or you excite the system with a step input. And then what you do is you look at the oscillatory or the time behavior of that system. So you have time as an independent variable, displacement or velocity as a dependent variable, and then try to see if this performance, this behavior, is it matching with the expected or the desired behavior. And clearly, many a times, the expected behavior is different than the actual behavior. So what we do is we add something called as a control. And with this control, we try to reduce the error. So reduce error. Now these specifications could be in time domain. A very simple example is I want this system to go to a particular point at this time, or I want the system to stop oscillating at this time, or I want the system to dampen out over certain period of time. So basically that is in the time domain. Second thing is in frequency domain. Now what do we mean by frequency domain? In frequency domain, we try to understand how does the system respond to input of varying frequency. And this is a very important distinction. So we want to find out how does system respond to changing frequencies. So to, I would say, input with changing frequencies. And this is a very important question because many a times system may not respond to the input that is supplied to. So system could either overshoot, undershoot, may respond, or completely go unbounded. So we need to know how does the system respond. And time domain and frequency domain analysis is very, very important for the linear systems. And the linear systems, they follow the principle of superposition, where means you can add the inputs and the system will respond with added outputs. And you can actually use the tools that we well know how to use to control, understand, analyze, simulate the system. Now, here are the performance specifications that engineers desire for. We want to understand first the speed of response, how fast the system is going to respond to a changing input. Then we want to find out whether the system is stable or unstable. And let me quickly recap, what do we mean by stability? So we talked about something called as the asymptotic stability. We also talked about simple stability. So simply stable. And we talked about unstable. So you have these three different types of stability. So we want to know whether the system is stable or unstable. The last thing we are interested in, how accurate the system is. And typically, this is characterized by something called as the steady state error. Now, I want to give you a very simple example. Imagine that this is the input. So I want my input to go to final value of 1. It is very rarely I would find a system that will track this response or this profile accurately. Most likely, I'm going to have a system that kind of goes like this, and typically it has a constant offset. So this is called as the constant offset. So think about it. You have a thermostat set up at 80 degrees, but air conditioner, since it's an on off control, please understand the air conditioning or refrigerator is sort of an on off control. It does not track it very well. So sometimes the temperature would go to 85 degrees, the air conditioner will shut off, it will let it go down to 75 degrees, it will turn on, and basically those oscillations will go back and forth to the point that you have a constant steady state error. And steady state error sometimes is tolerated, because if you want to minimize the steady state error, the control effort or the type of controller that you use could be either expensive or the hardware may not be able to support it. So here is a classic description of time domain performance specifications. And these performance specifications are defined in time domain. And typically, I want to emphasize on this. If you recollect, we have been talking about this model all the time. Mx double dot plus Cx dot plus Kx is equal to U of t. This is a fundamental model that is used to describe lot of mechanical, electrical, and electromechanical systems. Now, this is basically what this means is the system dynamics is governed by some type of an acceleration or inertial term. So this is, do we have an acceleration? You have a velocity term, you have a displacement term, and you have an external input. This is what it means. So system dynamics is characterized by an acceleration term, which is contributing to inertial effects. This is the sluggishness in the system. Inertial effects. Velocity term, these are the first order damping effect. First order damping effects. Then spring, which is the 0th order forcing effects, forces. And finally, you have an external input. So this is external. And even if the system to begin with is not in this form, we desire to put the system in this form because it is easier to analyze. Now what happens is we actually do a little bit of simplification on this. We divide left hand side and the right hand side by m, and this equation becomes x double dot plus c divided by m x dot plus k divided by m x is equal to 1 by m u of t. Now c over m is denoted at 2 zeta omega n x dot, and k by m is defined as omega n square x, and u of t is defined as u bar of t. This is called as the standard form. This is called as the standard form. Now, what we do is, if you have a system in the standard form, and if you excite it with a step input, and I need to be extremely careful when I make this distinction. Okay, I want you to understand how this works. So I want you to think about that this is the step input that is supplied. So this is time, and on y-axis I'm describing input and I'm describing output. So I have input and I have output. So if you have a system that is shown over here, then what's going to happen is it's going to go up, going to come down, going to go up, come down, going to go up, come down, and then it will have a steady state offset. And now if you have a step input that is supplied to a second order system, you can notice that there are certain features that is embedded in this output. So what are the most important features in this output? First and foremost, this is a unit step input. So I'm calling this a unit step input, which means the magnitude of step is 1. The response initially crosses this unit step input at certain point. Then it overshoots. Then it comes down, it oscillates around, and finally reaches a steady state. And you can tweak these behaviors or these features by tuning certain parameters. And now I want you to look at the equation that I have shown over here. And since external forcing u of t is known, is external forcing u of t is 1. It's a unit step response. Unit step response. If you look at the equation, there are 2 parameters that can be tuned. Which are these 2 parameters that can be tuned? These parameters are zeta, and the second parameter is omega n. Now, I want to emphasize at this point what is the advantage of putting the equation in the standard form. So let me give you a design problem. I want to design a system that behaves in a certain fashion. The equation for the system is described as equation 1. Equation of the system is described as equation 1. And what I want to do is, I want to find out the unknown parameters. So how many unknown parameters do I have at this point? At this point, I have a mass that is unknown. So m is an unknown. I have c that is unknown, and I have k that is unknown. Everyone agrees with me? As soon as I put this equation in the standard form, how many unknowns am I left with? 2, which means by putting the equation in a standard form, I have minimized the number of unknowns in the equation, and that makes my life very, very simple. Not only that, If you look at the second equation, which is shown over here, it's a non-dimensional equation, which means the units everywhere are numbers. They are just ratios. So it's a non-dimensional quantity. And finding out zeta and omega, it's easier. And once we do the control analysis, we will use the controller to controller tools, and that will tell us that how to find out these parameters. So let's understand what this is. So first and foremost, I want to find out something called as the rise time. Rise time means when the system goes to the desired value. In certain cases, you have rise time or you have modified rise time. Modified rise time means when the system goes to 90% of the desired response. So wherever system starts, and this is called as rise time, TR. Then you have something called as the peak time, when the system response peaks. So this is the peak time, TP. Then what you have is, you have something called as the peak value, which means the maximum value that the system goes to. Then what you have is percentage overshoot, which means how far the system exceeded to the desired set point in terms of percentage. Then you have something called as the time constant. The time constant is the time the system takes to reach is 66.6% of the final output. That is basically meant by the time constant. And then you have a settling time, when the system response settles to the 2% of the final output. So this is settling time. So TS. So these are the specifications. Now here is a quick idea. If I decide to design a system upfront, I'm gonna tell you that I need this rise time, I need this settling time, I need this steady state error, I need this peak value, overshoot, and so on and so forth. What we have to do is we have to take these specifications, use these equations, and find out appropriate values of omega n and zeta. So in time domain specifications, what we do is we supply the system with a step input, we understand the behavior of the system, and then we try to tune the behavior of the system in such a way that it meets with the desired specifications. Now, how do we do this? So let me take a very simple example. I'm going to work out an example by hand, and then I'm going to show you how we can use MATLAB to do some of these calculations. Say for an example, we have to design an automobile suspension. The weight of the automobile is 1000 kilograms. So this is the total weight of that vehicle. Equivalent stiffness at each wheel is 60 kilonewton per meter. So what we have is, we have spring, maybe we have this damping, this is the shock absorber, and then here there is a tire. And this is a quarter car model, which means I'm showing just one wheel. So the mass that is supported on this wheel is 1000 divided by 4, which is 250 kgs. And for here, on this suspension, the spring stiffness is 60 into 10 to the power 3. The the thing that I don't know, what should I tune this damping coefficient to so that the system behaves the way I want. So for an example, I want to find out the damping constant, but I would give you the performance specification for suspension. That is, it's 1% overshoot. Now, this is a very practical design problem. I don't know if you have driven the Mercedes vehicles with air suspension. The amount of air in the air suspension is varied depending upon the ride quality that you want, so that the damping coefficient is changed in runtime. So what happens is you change the air pressure inside the air dampers, and that actually tunes the damping coefficient. So the Mercedes suspension designers, they have specified that whenever somebody puts that vehicle into sports mode, then the percentage overshoot is very low, say 0.5%. If somebody puts that vehicle in a comfort mode, then you can have a little bit of more overshoot, but then the oscillations should be decaying over the period of time. It means you should have a smooth ride. So you can tune these parameters. And now, so if you look at the basic equation that we have, is this is the equation that we just said: my double dot plus by dot plus ky is equal to ku. And this equation is written into the standard form, which is shown over here. This is the standard form. And the advantage of equation is in standard form is you can use the equations that are shown over here directly to find out these parameters. So what is he saying? He's saying that the percentage of overshoot should be 1%. So what I would do is I will go here, pick up the equation for percentage overshoot. This is the equation. Put this equation over here and plug in the value for 1% overshoot, and then find out the value of zeta, which is 0.83. As we know, zeta is defined as C divided by 2 under root mk. In the last class, we derived this, the damping coefficient. Zeta is 0.83 is equal to C divided by 2 under root of mk. Once you do these calculations, your value of zeta is 0.83. That is going to give you, substitute 2, mass is 250 multiplied by 60 into 10 to the power 3. And then this is the value of C that you will get. Everyone understood this? So this is the simplest way of doing a times analysis, time spec analysis. Now what happens at the frequency domain performance specification? Now let's take the same example of automotive suspension. So we have this automotive suspension. And this automotive suspension, let me give you an example. There is a speed bump, or say you hit the curb. So you have a speed bump, and basically you gave a step input. So basically your automotive suspension was somewhere here, and then all of a sudden it was given a jump. So, and then what you want to do is you want to see how well this gets settled. So in this particular case, time domain specifications would suffice. Now, however, imagine a case wherein you have the vehicle that is going through a bumpy ride. So you have this vehicle, same suspension, and now this road is kind of bumpy. this road has certain wavelength, it's certain amplitude, and this vehicle has certain path, certain speed. So what that means is, if you visualize from analysis point of view, either the vehicle can be moving on the road and road is stationary, or vehicle can be stationary but the road can be moving, which means the frame of reference can easily be changed. So if you were to imagine that I have this road profile that I'm traveling at the velocity, which means that suspension is continuously sinusoidally excited, and I want to know how does this system behave to the sinusoidal input. Then the next question is, if the road becomes bumpier, which means what happens is this becomes like this. Imagine this road becomes like this. Imagine the road becomes maybe like this. So how is the system going to behave when the same suspension is gonna ride on roads of different profiles at different speeds? So that question is answered by this frequency domain performance specification. So frequency domain performance specifications are super important when you have a system that is excited by the input, which is of varying frequency. Everyone understood the setup here? Any questions? So what does these two plots tell me? These two plots are called the body plot. The body plot is, here is what I'm going to do. I'm going to attach maybe a displacement sensor. So I'm going to measure a displacement. So displacement, measured displacement. And then I'm going to run this vehicle at certain speed. So which means that will be certain frequency. And at that frequency, I'm going to find out, hey, how much is the displacement? Then I'm going to run that vehicle at a higher frequency or higher speed. And I'm going to say, hey, what is the frequency? I mean, what is the response? So this is the magnitude or the displacement, and this is the frequency of input. You would realize at certain point, at certain frequency of excitation, the response of the system starts increasing. So system response increases, and then after some time the system response decreases. The classic example that I talked about in last class is washer. If you have the washer set on spin cycle, at certain low spin speeds, the washer does not vibrate. As the speed increases, washer starts vibrating. At critical speed, washer vibrates violently and perhaps walk away. And then gradually, as the speed is decreased, washer settles down. So the response of the washer is a dynamical system described by spring, mass, and damper, is dependent on excitation frequency. The next thing that we talk about is the phase. And what is the concept of phase? Now, this top plot is gonna just give me the information about magnitude. It does not give me any information about how quickly or how sluggishly system responded to input. So phase is the difference between the input and the output. Say for an example, if your input is sinusoidal, Now I want to ask you this simple example. I want you to think about, let me give you a very simple example. I have system that does not have any mass, no mass, just spring. Okay, massless spring, hypothetical massless spring. And if I excite this massless spring, and if I measure the displacement of the massless spring using some type of a laser distance measurement, or maybe an accelerometer, or some type of measurement technique, optical technique. My question to you is, what do you think will happen? So I'm saying that let's excite this system like this. Now my question to you is, how would this the system respond based on your experience? It will also oscillate, but it is super important to note that the phase would be 0, because this system would track the input exactly. Everyone understood this? Because this is a 0th order system. Everyone understood this? So I give you a very simple example. When my daughter was born, when she was a very small baby, she would cry and everyone would run to pay attention. Hey, what's going on? Do you need a diaper change? Do you need milk? Do you need something else? Or are you uncomfortable? So like, think about it like the 0th order response. There is input and all of a sudden parents come running down. So that is a 0th order response. As she grew older, when she became toddler, she became maybe high toddler, then she would say, I'm hungry. Then probably we would say, wait for a minute, we will give you something. Okay, so there was a delay in the response. That is the typical characteristics of a first order system. So which means instead of the spring, if you add a damper, and if you repeat that exercise, not the daughter, but with the system, so you would observe the system response is going to be lagging. So which means because of the damping effect, you are going to have some type of delay. Now, when my daughter is in high school, she says, yeah, I'm hungry. What do we say? Come on, you're old enough. Go get a snack yourself. So now this is like you have a second order system, which means your response could either be lagging or it could be leading. So think about it like now you have spring, mass, and damper system. Now it is this leading and lagging is kind of a funny thing, and I think it needs a little bit of specification, a little more specification and discussion. So what we are looking at is we are looking at a sinusoidal waveform. It's a periodic waveform. Why do we call it periodic? Because after some time it repeats. Do you agree with me? After some time it repeats. So if you think about it, this is something called as the 0 degree. This is called as 360 degrees. Do you agree with me? Now what I'm going to do is I'm going to start delaying. Okay, so I have some delay, some more delay, some more delay, to the point that my delay is 1 cycle apart. My delay is 1 cycle apart, which means my delay is delayed by more than 360 degrees. So what happens when the delay is delayed by more than 360 degrees? For a minute, ignore this part. If you look at the second cycle, you would notice that as if output is leading the input. And this phenomenon happens because of the periodicity of the input, not because it's getting delayed. You delay. You delay to the point that it is that delay is causing the response to be ahead of the second input. So when you actually look at the system, you will actually feel like the system response is advancing. So basically it's leading. So again, that is the basis of designing lead and lag compensators that we will talk about later. Now clearly engineers hate non-linearities, because as soon as we have these non-linearities, the system response could be weird, unpredictable, or outright chaotic. So these are the different types of non-linearities. They basically shape the input in such a way that sometimes you can predict, sometimes you cannot predict. So what we do is we try to minimize the non-linearities. Non-linearities cannot be fully eliminated, but non-linearities uh, can be minimized. Now here is something I want to talk about, the advantage of non-linearity. Nowadays, you must have seen all this big discussion about machine learning, neural network, artificial intelligence. What is all that in a crux? So basically, here is what it all deals with. You have an equation of a straight line. So y is equal to mx plus c. Everyone okay? Y is equal to mx plus c. That is the equation of the straight line. X is the input, Y is the output. X is the input, Y is the output. In high school, we understand M is the slope. Do you agree with me? M is the slope. And C is the Y intercept. Do you agree with me? In neural network, the exact same equation, Y is equal to mxc, is rewritten as M is the weight and C is the bias. And that is how one neuron is specified. One neuron has an input X and an output Y. Now what we want to do is, we want to approximate a behavior or a nonlinear function using this neuron. Idea is, a linear system cannot completely define the nonlinear system. So you want to add some type of nonlinear element to it. So what we do is, basically this neuron is fed into an activation function. This activation function, believe it or not, it could be something like this, and that is called as ReLU, or it could be something like this. This is called as the tan H, or people have experimented with the hysteresis type, the nonlinearity. So what that means is, once you have this system, you have a linear approximation, you have a nonlinear activation function, you can approximate a nonlinear input to output relationship. That is the crux of neural networks. Now, if you think about, you want to approximate a super complicated nonlinear relationship. Clearly, what I'm going to do is, I'm going to actually write this with multiple layers of neurons, which will be comprising of one neuron, second neuron, third neuron, fourth neuron, either in a straight line, or I could have those cascaded, or I could come up with some exotic arrangements of these neurons. And at the end, what I would do is, I would give an input, measure an output. If they don't match, then I tweak these gains. So I change the values of M, I change the values of C. I don't change the activation function. I only change the values of M and I change the values of C, to the point that I have a perfect reconstruction of input to output relationship with this neuron structure. That is the crux of neural networks. Neural networks utilize the nonlinearity and the linear equation to create a universal approximating function. Everyone understood this? That is what a neural network is all about. Okay, so nonlinearity is super important. Now, what are Any questions from my online students? Everyone clear so far? Okay, now next part, which I want to quickly talk about is, so how do you eliminate the nonlinearity? And again, I want to emphasize on these concepts when we actually deal with control and the labs, but nonlinearity can be minimized using either calibration, using feed forward controller to get rid of nonlinearity, changing the operating range, minimizing friction, stiction, and basically making sure that the backlash or other mechanical nonlinearities do not exist, or at least minimize. Then in the last class, I reviewed these important concepts on instrument rating parameters, wherein the sensitivity, dynamic range, resolution, drift, frequency range, bandwidth, and impedances are super important. Now, what I want to do is, I want to basically talk about this bandwidth a little bit, because bandwidth is a little bit of confusing term. If you talk to a control engineer, bandwidth means something. If you talk to a communications engineer, the bandwidth means something else. If you talk to a mechanical engineer, bandwidth means something else. If you talk to a very busy business professor, bandwidth means something else. Hey, I don't have bandwidth for this type of work. So basically, bandwidth means different things for different people. So what is bandwidth? If you talk to a control engineer, bandwidth means the useful frequency range. Now, use is defined by that person. Say, for an example, if you talk to a controls engineer, he will say, this is the bandwidth of my filter, which means my filter would work only in this frequency range. If you talk to a mechanical engineer who has designed suspensions, he will talk about bandwidth means my system would work in this, it is that minimum frequency, it will work at this maximum frequency, but I don't know about the response in between. If you talk to a very busy person, do you have bandwidth for this job? He will say, no, I'm completely booked, I do not have any bandwidth. So bandwidth is typically the speed or the frequency at which the instrument can operate successfully. We talked about the linearity in last class. I showed the exact same plot. This is the linear approximation that we are going to deal with, and we want to make it as linear as possible so that the system response is predictable. And these are some interesting definitions of bandwidth. And then you have something called as central bandwidth, which means this is the operating frequency at which you want your instrument to operate. So even if the frequency is a little bit lower or frequency is a little bit higher, the instrument can still function. And many a times, if you look at the digital communications, bandwidth is given in terms of the samples per second or the signal generation, the amount of frequency the signal can be generated. And there is something super important, that is Shannon's sampling theorem. And I talked about it in last class. I briefly talked about, but I want to actually emphasize on this because this is sometimes not discussed very clearly. So please try to understand that if you have, I will start with the example that I discussed in last class. Imagine that you have a signal that is varying something like this. Okay, and if you want to discretize this signal, which means this continuous signal needs to be sampled, and if you want to kind of express that as snapshots, if you take snapshot at this point, if you take snapshot at this point, if you take snapshots of this point, you take snapshot of this point, this is what you're gonna see. So somebody would say, hey, the system is not responding at all. And because the snapshots are not at the right frequency, you are not taking the snapshots at the right frequency. So what if you want to reconstruct this, what you need to do is, in addition to taking snapshots at these points, we have to take snapshots here, 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 and here. Then we can actually add the missing piece of information. And clearly, this is not the good data capture, but at least it shows me the trend. You agree with me? So what it means is, for proper reconstruction, the sampling frequency has to be twice that of actual frequency. So sampling frequency needs to be 2 times of the actual frequency. Now let's understand what happens if I decide to come up, if I have a signal, and this is a very important point. If I have a signal that is running at say 100 hertz. Okay, I have a signal that is running at 100 hertz. So I'm sampling it at 100 hertz. So this is, I'm going to call this a sampling frequency. And then what I do is I do something called as the Fourier transform. So I do Fourier analysis. Now what happens in Fourier analysis, I kind of have the frequencies and I have the amplitudes. And basically I'm going to have, so these frequencies will go from 0 to 100 hertz. And I will try to find out, or you will actually do it with number of bins. You will find out the spectrum, and this spectrum maybe look something like this. What that aliasing means is, if the signal is sampled at 100 hertz, and if you plot the Fourier transform, you cannot trust the output after 50 hertz. So this output, as a matter of fact, the output that is close to 50 hertz, you cannot trust, not to be trusted. And here is the reason why. What happens is, there is the concept which is called as aliasing. Aliasing is basically, you can think about it, it's like the fold over of the frequencies beyond the half of the frequency. What that means is, say if you have a signal that you are sampling at 100 hertz, and don't think that this signal is a very clean sinusoid. Okay, think about it like this signal has sinusoid, a super complicated signal, and this super complicated signal has frequencies. This super complicated signal has frequencies all the way from 1 hertz to say 70 hertz. So you have this super complicated signal that is like combinations of frequencies that are going from 1 hertz to say 70 hertz. You are sampling this frequency. Now, what do you mean by sampling? Is basically what you do is, you basically take this teeny tiny snapshot. So 100 hertz means 100 times a second, 1 divided by 100, which means 0.01. So every 0.01 second, you are actually capturing a discrete point, a snapshot. Every 0.01 second, you are capturing the discrete snapshot, and then you feed that into your FFT, some type of Fourier transform algorithm. And once you feed it to FFT, you are going to get these nice plots. You're going to get these nice peaks. And if you follow what we talked about, FFT will give you frequencies and amplitude. So you say, hey, good, I have a signal which is at 1 Hertz. I have a signal which is at 30 Hertz. And then if you go and say that, hey, I have a signal at 50 Hertz, you have to question this outcome. Because what has happened is you are not accurately capturing the frequency content of the signal because of the fold over of the frequencies beyond 50 Hertz. Which means what would happen is, if I want to use the FFT, I would only say that I only am sure about in the range of 1 to 30 Hertz. I do not know what this plot is showing me after 50 Hertz.
Is it after 50%?
After half of the frequency. So, and this is super duper important, because many a times what you do is this. What I'll give you a very practical example that happened to me. So when I was working in industry, I had a very interesting problem to diagnose. So there was a machine. It was a shaker, and what is shaker supposed to do? Shake, right? But it can't shake at the frequency that it wants. It has to shake at the frequency that we program. So that is the purpose of the shaker. So what happens is, we had this shaker and it used to work fine, but as it got old, then it started to behave weird, and we wanted to see where the problem is, because that's an electromagnetic shaker. It again has the coupling, it has a blower, it's a mechanism to cool. So you have a lot of these rotating parts, moving parts. So we want to identify where exactly the problem is. Please understand, all these parts vibrate or rotate at different frequencies. How do you pinpoint which part is bad when you have this integrated system? The classic way to do it is, put an accelerometer on that shaker table, get the vibration signature, do the FFT, and see which are the most dominant frequency. Ideally, the most dominant frequency should be the program frequency, the frequency at which we want that shaker to vibrate. If the shaker is not vibrating at that programmed frequency, which means something is wrong. And then the most dominant frequency is the frequency associated with some other moving part. And then we see whether it's a blower, whether it's a cooling jacket, or whether it's a pump, or whether it's some coil or some magnet, whatever it is. But then what started happening, that we started to vibrate shaker. We tried to do a sine sweep. We tried to vibrate the shaker at 60 Hertz, 70 Hertz, but the accelerometer we used to capture the data was capturing data at 100 Hertz. So the frequency spectrum that we got for the diagnosis of that shaker was incorrect, which means from the frequency spectrum, we say, hey, we have this huge peak at 80 Hertz, or we have this huge peak at 40 Hertz. But you know what? There is nothing in there that operates at 80 Hertz. So what do we do? There is nothing in there that operates at 40 Hertz. What do we do? Then the whole issue got resolved when we got an accelerometer which could sample at 1000 Hertz. And then we sampled the data at 1000 Hertz. We did the FFT, and at that time, we could see that, yeah, this is where the problem was. So aliasing is super duper important, and you see that many times in industrial applications. So whenever somebody asks you to understand or simulate or investigate a power spectrum, then make sure that aliasing is not hampering your result. So what is how do we minimize aliasing? So there is something called as anti-aliasing filter. Anti-aliasing filter is nothing but a very simple low pass filter that would actually filter the data so that all the higher order frequencies, the frequencies beyond 50 hertz, are eliminated. So this is the standard procedure, and remember this will save you a lot of headaches. So you run the system through a low pass filter. So say you have a sensor that is getting the data at 100 hertz. So you have an accelerometer, or you have some type of a sensor that is getting data at 100 hertz. You set up a low pass filter so that all the frequencies less than 50 hertz can go through, and then pass this data to FFT, and that would minimize your aliasing problems, and whatever you get is going to be accurate on the frequency spectrum. Everyone understood this? This is super practical, so please pay attention to this. If you have to do something what I did, like machinery vibration diagnostic, prognostic, or if you want to design the suspensions, if you want to study the engine behavior, a shock vibration analysis, then always think about using anti-aliasing filter. So this is what happens because of the aliasing, that is also called as the folding, which means the high frequency component, they get creeped into the low frequency spectrum and they distort the low frequency spectrum. So basically you can't trust that spectrum anymore. How do you reduce aliasing? The most important part is to add a low pass filter which is less than half of the sampling frequency. Now, we talked about instrument error analysis in last class in detail. So we want to make sure our instrument is accurate and persistent, repeatable and accurate. So we have the precision and we need to make sure that the instrument is accurate. There are deterministic errors, which are offsets. There are random errors, which are basically stochastic or vary. We combine errors multiple ways. We can just add those. That's not the most right way to do it. Or you can do sum of squares, square root, or you can do absolute. There are different techniques with the errors can be combined. Now, dynamic range is basically let me take a very simple example. So this example comes from the textbook. But before I start solving example, I want to ask you if there are any questions on the material that we discussed so far. Any questions, concerns, doubts? Okay. So imagine you have an analog to digital converter. What does A to D do? A to D would actually sample the data and separate that data into bins. So basically, if you have a 12-bit A to D converter, then you have 2 to 12 bins to separate out. And the dynamic range is basically given as the range of operation divided by resolution. Since A to D start with 0, you actually subtract 1. But basically, even if you don't do it, their answers are not going to be different. So basically, 2 to the power 12 log of 10 multiplied by 20. This is the 72 dB resolution. And you will call this like decibel. This is called as decibel. Does anyone know the story behind this decibel? So when the Bell telegraph company started, what they were trying to do is they were used to have phone lines. This is phone 1, and the other phone line, phone 2. And what they wanted to see is, what they did is they put an amplifier here. What does this amplifier do? Simple words, this amplifier would increase the amount of current so that the current can flow from point A to point B. So you have this telephone, so no cell phone, just wires telephone, and you have another telephone over here, and they wanted to know the transmission loss. So what should be the input magnitude of the sound so that the output magnitude of the sound is within the reasonable range. And believe it or not, when initially those analog telephones started, these noises were huge, the losses were huge. So think they had to, so the person who is on the talking side and the person who is on the receiving side, if they were to talk in their normal voice, the signal will not go from point A to point B. So what they had to do is, after the person talks, that signal is amplified. Think about it like an amplifier. And then that signal is amplified signal, large current gets fed from point A to point B. And by the time it goes to point B, it loses its strength and its losses, and then it is respectably audible range. So they wanted to know this huge amount of signal finally became this very teeny tiny amount of signal. These losses were huge. So that's why they came up with a logarithmic scale. Like what is the output divided by what is the input. So basically these ranges were very, very high, very, very large. So they wanted to come up with a log measure, because here's what happens. Human voice is not at a constant frequency. The frequencies vary, which means if I talk or if someone else talks over the same transmission line, the amount of losses are going to be different. So they had to characterize what happens, what is the loss at 10 hertz, what is the loss at 20 hertz, what is the loss at 30 hertz. So basically do a sine tune or sing at 10 hertz, ting, 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 have a monotone at ting, 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 ting at 10 hertz, have a monotone ting, 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 ting at 20 hertz, and see what is the amplitude that you receive at the receiving end. And they wanted to see, and you will see the range would be 1 to 10,000. You cannot plot these on a single scale, a linear scale. So they created this log measure that could take this wide variation and fit into a reasonably representative graph. That's why this the Bell unit came into existence. But Bell unit was essentially quite large. So decibel is a fraction of that Bell unit that is currently used in all control systems, communications, and data analytics. Everyone understood this? Okay. So the next part is, this is a very simple example wherein what you have is, you have a damper, you have a torsional spring, and you have a shaft. And there is a pointer where here, so, and this pointer is rotating. So what we want to do is, first and foremost, if you think about it, this dynamical system can be expressed at the same expression that we talked about, a spring mass system. So you have the spring mass system that is describing the motion of the pointer. If you take the Laplace transform on the left hand side and the right hand side, what you can do is you can come up with this nice transfer function. So this is the transfer function of that instrument. So this is the dynamical model of the instrument. This is the transfer function of the instrument. So I'm going to stop here for 15 minutes and then we will be back. We're going to talk about control systems. It's a very important topic. And if you ask me, the two most important topics from this textbook, and that's why I intend to cover them in the very beginning of my courses, is chapter 2, which is dynamical systems modeling. Then next national core chapter is chapter 5, that talks about the performance specifications for the dynamical systems. So you have modeled the system. Now you want that system to behave in a certain fashion. That is where the performance comes in. And then how do you ensure that the system behaves the way we want? And that is where the control systems come in the picture. So basically, what is the objective of control? So from chapter 2, we have come up with this dynamical system. So this dynamic system that we derived, and we studied this dynamical system in chapter 2. Now what we want to do is, we want this system to behave in a certain way, and that is described in this performance specifications, that how do we want this system to behave, whether it should respond quickly, whether it should respond sluggishly, it should be robust to the disturbance, or it should be very agile, so like F16. And then in this chapter, we are going to talk about how do we control the system so that it behaves the way we want it. And this control problem is not trivial, because just to give an example, the system usually are super complex. Think about an aircraft. The aircraft has aerodynamic excitation, so wind loads. It has the body excitations, the vibrations. Then it has the control surfaces like aileron and rudders excitation. And sometimes these excitations are known, sometimes these excitations are unknown. Many a times, if the aircraft is flying in a level flight, it's like ride is smooth. But all of a sudden, if it hits in a turbulent zone, or if there is a bird impact or something like that, the dynamics will be totally out of ordinary. Then you will have certain unknown parameters. So for an example, how the aircraft is loaded, what is the weight distribution of the cargo, all these factors, they play an important role. And these are the uncertainties that engineers have to deal with. So why is this super important? Let me tell you that when you go to industry, control design is a critical component of robotics industry, manufacturing industry, automation industry, automotive industry, or electronics industry, and so on. So because all the dynamical systems, no system comes the way we want. We put together a system, we try to study the system, we test the system, we understand that system is not behaving the way we want, we design a controller so that system behaves in a particular fashion. Sometimes the controller could be present, or it may have to be specifically designed and integrated. So the system can be, you can actually design it specific to certain requirements, or sometimes they will give you, this is the system that you have to deal with whatever you have, but make it work and meet the next set of specifications. Sometimes the designers make mistakes, and this is actually very, very important. Okay, please try to understand that compensate for design weakness, not only design weaknesses, but design, sometimes designs just get old. For example, you have a manual car, and now you want to make it autonomous. This is something that the designer of the manual car didn't think about. But right now, there are industries, they are focusing on this particular problem. You have this car, this is designed to be a manual driven car, you need to make it smart. So how do you retrofit the old car with its new sensors, new techniques, new technologies, so it can work as an autonomous vehicle? And as a matter of fact, let me tell you, no way, no vehicle, very recently they started doing it. No vehicle was designed to be autonomous to begin with. What these companies like Waymo, Uber did, they got the cars that were supposed to be designed by, driven by humans, and they retrofitted that with all this instrumentation to make them driverless. But then gradually, as the industry shifted, the companies like Tesla, they started designing the cars from ground up so that it can have this autonomous driving capability. And as the softwares and algorithms and techniques and systems, they get better and better and better, then basically you will see the cars, and those cars will not have steering wheels because there won't be any human intervention. It will be, there won't be any brakes. Right now, the cars that we see that are driverless cars, they all have all these means for driver interventions. But as the technology matures, as we know more about it, as we make these cars safer and better, then these technologies would be really become completely autonomous. Now, recently, I had a very interesting discussion with someone who works in this autonomous vehicle span. And some of you, if you are trying to think of getting into that exciting field, I will strongly recommend that the next wave of robotics engineering in autonomous cars is going to be development of cyber secured autonomous cars. Because right now, the legislatures, right now the designers, right now even the users are afraid that these cars may not be secured. There might be many entry points of attack. I would give you a very simple example. The cars use LiDAR, but do you know that LiDAR can be rendered effectiveless with a very cheaply built jammer? So the LiDAR basically you can have laser diodes which would actually blind the LiDAR, so to speak. You could have cameras, and then what you do is the cameras, you create an artificial environment around the camera. That way the camera would misinterpret the surrounding. You could have some type of, the vehicle area networks. Nowadays there are these over-the-air updates to these cars. You can send an over-the-air update that would hack into the ECU of the car, and you can make that car into something very dangerous. So if you are interested in becoming autonomous in driving or autonomous vehicle engineer, if you want to become even a software engineer in that area, in next couple of years, this is where the jobs will be. Because right now, everyone is working on building autonomous cars. But unfortunately, the cyber security, making these devices secure, is not caught up yet. We need new tools, new techniques, new architectures to make these cars safe. Now, same thing happens in the case of Predator drones. Those are autonomous drones used for military vehicles. But please try to understand, it is very difficult to hack into a Predator drone because of the communication protocols are so restricted. Not everyone rides or drives or flies Predator drones, right? So we don't have thousands and thousands of autonomous drones flying around, but we anticipate that we are going to have hundreds and thousands of autonomous vehicles on our roads. Those vehicles should be safe to the passengers, they should be safe to the environment, they should be safe to everybody around them. So if you are interested in looking for what would be the next wave in robotics, So let me tell you right now that that is where the industry is headed. Next year, you will see tons and tons of jobs and opening for roboticists, control engineers. They have background in cybersecurity, how to design the secure embedded systems so that people cannot hack into, or how do you make the systems that are hardened against the threats. So that is super important because you want your system to be stable, you want your system to be accurate, and you want your system to be responsive. But at the same time, you want your system, which is not said over here, you want it to be secure. You don't want that someone can just hack into your car and then drive it away. Or yeah, do something that no, we don't want it to do. Or instead of taking you to point A, it will take you to point D. And imagine our kids are riding in that autonomous car. We want the kids to be dropped at the school, and guess what? The kids get driven somewhere else. We don't want that to happen. So if you are looking for a career, start thinking about developing cyber secured robotic systems. That is going to be super duper hot. Or cyber secured automation systems, because with this industry 4.0, we are coming up with this connected industries, wherein you will have one industry here, one industry in Brazil, one industry in France, and all these industries, all those manufacturing will be connected over internet. So you want to make sure that everything works seamlessly. So I would strongly recommend that you get a little bit exposure to cybersecurity, framework of cybersecurity, cybersecure robotics, and so on. And if there is significant interest, I would be happy to teach a graduate level course in cyber secured robotic systems, but I would need about 30 students to offer such a course. Anyway, that being said, what are the applicable aeronautic, the fields where the controls are used? Controls are used in aerospace and mechanical. They are used in civil. They are used in chemical processes. They are used in electrical. They are used in materials engineering, mechanical engineering, mining, and nuclear engineering. All the industries that serve humanity, the control engineering is present. What is the common taxonomy or terminology in controls engineering? You have something called as the plant or the process. That is the thing to be controlled. You have inputs, that is the excitations. You have the output, which is the response. Sensors are measuring things. Actuators are driving or controlling things. Controller is actually a hardware, and control law is a software or logic that is implemented on the hardware. And the control system comprises of all these things. Like you have plant, controller, could include sensor, signal conditioning. You could have a feedback control. You could have an open loop control, or you can have a feed forward control. And all these controls are utilized independently or together to achieve what we want to achieve. So you can have a control signal that is determined using actual control response. In the open loop, you do not have any feedback. So think about it. I teach everyone mechatronic systems, but I don't look for any input from the student. So I just come here, teach blindly, and then do nothing. Or I could be running it in closed loop, where I will ask students question, make sure they understand, and if some part is not understood, go back and revisit that content. So that is open loop. In the feed forward control, this is an interesting idea of feed forward control. So what is feedback control? Feedback control is looking at the output, sampling part of the output, and tuning the input so that the desired output is achieved. What is feed forward? Feed forward is overcoming the disturbance without sampling the output. I give you a very simple example. Imagine all of a sudden, here is that air conditioning humming sound in this room. All of a sudden, if that sound increases, what would I do? I would raise my voice automatically. I would raise my voice automatically because the external disturbance has increased. So that is what is feed forward. Because here is what I would anticipate. If I just talk at the same voice and this air conditioning noise increases, then probably you may not be able to hear me well, which means that will affect your understanding. So in anticipation of that, I increase the volume of my voice. So I'm feeding forward to take care of the external disturbances. Same thing happens in controls. This is how the structure of a control looks like. You have something called as the plant. You have signal conditioning. You have a feedback that actually samples the output, and the whole thing gets fed to the control algorithm. So if you were to think about the human system, our brain has the hardware, our thinking is the software, eyes and ears are the sensors, hand and legs are the actuators. So that is the control system. So a control system, this is the classic definition of control system, has actuators, sensors and transducers, and these are the different systems wherein you have different sensors, you have different actuators, and these sensors and actuators either could run in a closed loop or they could be controlled in an open loop. This is the classic closed loop control system architecture, wherein you sample certain part of output and you feed that output all the way back to the reference. You compare it with the input, that is called error. That error gets fed into control law, and then you use an actuator to control the plant. And you do it recursively till you meet particular performance specifications. Now imagine this is a classic example. If you are driving a car, then you are seeing the road where you are going, that is sensor, you are controlling the throttle and steering, that makes sure that you follow the path and go to the places where you want to go to. In an open loop, there is no feedback. It's basically you just give an input and hope that that would result into proper output. You don't check. So that is what is an open loop control. In the feedback control, you have an output, you sample, and that's get fed to the controller, and you have the error, and that error is utilized to control the output. So basically, this is the simple fundamental principle behind the control. So let's think about it, that you have an input, you have an output, and what you do is the part of the output gets fed over here, so y of t, and then the difference between u of t and y of t is error, which is e of t. And what you do is this e of t you can multiply with a constant, that becomes proportional control. You can multiply that with a derivative of error, that becomes the derivative control, or you can control it with an integral of error. So this becomes P control, this becomes D control, and this is I control. So you have proportional control, you have derivative control, and you have an integral control. And you have this very simple on off, which is called the bang bang type control. So you have this bang bang control. You turn the system on, you turn the system off. You can have a proportional control, just add proportions, or you can have a proportional control with an integral and derivative control. Unfortunately, the analog controls are nowadays they are not used. So we most of the times use something called as the digital controls. So in digital control, what you have is you have the signal conditioning and amplification block. You have a computer, which is the code is working, and then you have the sensors and actuators, and you sample the response from the sensors and actuators. And if you run this system very fast, then you can approximate the digitized output to be equal to analog output. There is something called as the feed forward control, wherein in the feed forward control, you adjust the input so that the unknown disturbance is already compensated. So basically somehow you can have this unknown input, and then you compensate for that by tuning the input. This is a very simple example for a water heater or boiler, wherein what you have is you have the furnace, you have the boiler, and then you track the temperature using a thermostat, and then basically turn the valves on and off and reduce the intensity of the heat to the water and adjust the amount of steam and the temperature of the steam. So what are the control techniques? So there are time domain control techniques. So basically what you do is you do the control in the time domain. Then there are frequency domain control techniques, wherein you use transfer function. You can use servo control, wherein you actually want to track a particular trajectory. And you can use state space control or multiple input, multiple output techniques. So basically you have state space control, you have servo control, you have frequency domain control, and you have the time domain control. One step further, you have something called as the optimal control, wherein you want to minimize certain effort or certain cost using certain mathematical tools. Or you can actually control using the pole placements or changing the locations of the eigenvalues. Then there is LQR control, linear quadratic regulator, which is optimal control. There is linear quadratic Gaussian control, which is called LQG control. There is a nonlinear control. There is an adaptive control. There is model reference control. There is a sliding mode control, and there is H infinity control. And I just want to give you a quick input here that all these control laws can be implemented on TC Lab. So we are going to start TC Lab with a simple bang bang and PID control. Bang bang control is turn on and turn off and see the performance. PID control is add the proportional derivative integral term and then make that control behave the way we want. And then once we are towards the end of this chapter, because this chapter and this textbook only talks about linear techniques, then I'm going to teach you some of these advanced control techniques that would be super duper helpful when you go to industry. Because in industry, once you are going to design a control system, sometimes you have to use linear control, sometimes you have to use non-linear controls, sometimes you have to use the combination of both controls. So once we go through some of these simpler linear control techniques, we will talk about the advanced non-linear control techniques, and we will perform the experiments using the TC Lab, wherein we will implement these different control approaches. Okay, that being said, then you can actually, if you are into neural network, fuzzy logic, machine learning, you can actually use some knowledge representation techniques to come up with intelligent control, fuzzy logic control. And at the end of the day, this is what we want our control system to do. At the end of the day, this is what we want to do. We want our control system to be stable. It should respond if we want it to be asymptotically stable, it should be asymptotically stable. If you want it to be simply stable, it should respond as a simply stable. It should be super fast. It should not be sluggish. It should not take 10 minutes to respond. Then it should be low sensitive to noise or the disturbance. So it should ignore the inputs that are not important, and it should respond to the inputs that are really required. So it should be highly sensitive to control inputs, and it should be accurate, and it should actually have very low error. So these are the different parameters, and these are the desired values, and this is the purpose. And the most important part is these are the specifications that we studied in chapter 5. So you have an attribute, say stability level. You want system to be highly stable. What does that do? It means the response does not grow without limit. So what are the performance characteristics that you are going to specify to make sure the system is stable? And those are percentage overshoot, settling time, low eigenvalue or low placements, time constant, damping ratios, phase and gain margins. These are the performance specifications from chapter 5 that would help us ensure the stability that we are looking at. The next thing is the speed of response. We want it to be super fast. So plant should respond quickly to inputs, rise time, peak time, delay time, natural frequencies, resonant frequencies, and bandwidth. These are the specifications that you want. Steady state error, it needs to be low, and error tolerance for the step input is the indication of the steady state error. Robustness, input noise tolerance, dynamic interaction, cross sensitivity, and cross transfer function. And these are the discussions of different performance characteristics. And this actually is the review of chapter 5. And what I'm going to do is, with this, I'm going to go to the TC lab. So at this point, I want you to get your TC lab experimental setup ready. So everyone online, please get your TC lab setup ready. So I'm going to turn my video, and I will try to set up my TC lab. I don't know if you can see this. Please let me see if I can do it with this Zoom. So it's the first time I'm doing this, so bear with me. As I said, it's always challenging. Can't see. Oh, needs to be in this orientation. Can everyone see my TC lab? So connect the TC lab. So this wire, it's connected, is the power. And second part is the Arduino. We are going to have this DC Lab setup. So you'll have this DC Lab setup. And then once the TC Lab is set up, I'm going to share my screen. I want you to go, let's see how this works. I want you to go to my screen and go to the TC Lab folder that we opened in last class. There you got this all TC Lab stuff. There is this MATLAB, there is this Simulink, there's single hitter. So what I want you to do is, in this single hitter, I want you to look at Arduino Lab 2016A. Please open Arduino Lab 2016A, or you can open, for that matter, Arduino Lab, just the Arduino Lab. Open this. So online students, I have a quick question. I have this experimental setup. Are you able to see my experimental setup on the side? Oh, fantastic. So it worked. So you should see my experimental setup. And you should be able to see my Arduino Lab as well, right? I mean the Simulink folder. Okay. Now what I want to do is, this is the lab. Before we do the control, I want you to run this lab just to make sure that everything is working. Please run this to make sure everything is working. So you should see, I don't know if you see this, but one of one would get pink here. I don't know if you can see this. One would get pink. The other one is black because that is turned on. It's the thermal paste is turning pink. And after some time, the LED will turn on because it will get hot. LED will turn on. Everyone, is lab working? Graph is not showing? Okay, I'll be there. Okay, now what we are going to do is we are going to design a controller for this guy. Everyone with me so far? Any questions? Is it working, not working? First step is stop this. Second thing is save as. So I'm going to call this Arduino Lab test. Save. Then I'm going to take this block out. I'm going to take this block out. I'm going to take this out. I'm going to take this out. I'm going to take this out. And I'm going to take this out. Then next step is I'm going to control, I'm going to double click here, properties, mux block. And what I want to do is I actually don't need a mux. So actually I can delete this. And now what I can do is I can actually connect this to this guy. Now what I have is I have a simple system. Do you agree with me? Actually, you know what? Let me add a mux block. So linear in the newer versions of MATLAB, I can actually add. Okay, let me see. So basically, so you commonly use blocks. I can use mux and demux. So yeah, I can grab this and place it over here. Delete this. I put it over here. Now what I'm going to do is I'm going to have a temperature here, and then I'm going to have this guy connected to the set point. Everyone with me so far? Online students? What? Click and delete. Click on that block and delete. I'll be there just a second. And as you can see, if you run this, can someone tell me, is this an open loop or closed loop system? Can you see that blue line? This blue line is the set point. And this yellow line is the actual temperature. Are you with me so far? So this system is in open loop. And clearly, even though we want it to be at 40 degrees, the temperature is at 50 degrees. Do you agree with me? And it is fluctuating. Online students, did you get the same results? I'm gonna stop. Online students, any questions? Now what I'm going to do is I'm going to add a control. So to add the control, I'm going to go here, get a sum block. And what I'm going to do is I'm going to measure the temperature from the system. So so the way I'm going to do it is plus minus I would take this out from here. I would take this out from here. I'll put it over here. So this needs to go from here. Let me do it like this. First, feed this here. Feed this here. So this guy needs to go here. This guy needs to go from here. And I'm going to get a feedback from here. And this is going to be over here. Are you with me so far? And then I want to know what is happening here. So what I could do is I could actually extend this mux and so basically block parameters. I would say number of inputs 3. So what I'm going to do is I'm going to take this error term and attach over here. So right now what we have is we have a simple feedback control. Are you with me so far? And I'm going to run this code and see if it works. So you can see that 40 degrees is the set point. and this temperature is gradually coming down. That is telling me that the PID control is gradually, the P control is working. This is proportional. And you will see this error. So this error should go to gradually should go to 0, and finally the control should go to, can you see the proportional control working? Is it working? So this is the error. Initially the error was huge. In the proportional control, the error is approaching 0. This is the set point for the original output. Now its output is tracking. Fun, right? So because we have to. Yeah, you have to stop before. Now can you see that error overshot? So it's actually coming down. So can someone tell me what is the problem with this proportional control? Is there any problem with proportional control, or is it clearly it is not responding quickly? Then there is overshoot and the response is sluggish. So how do we make it better? So the easiest way to make it better is, as you can see, that there is no constant of proportionality. So add a gain. So what I will do is basically add a gain. So let me see. Yeah, add a gain. Right now, my gain is unity. So what I'm going to do is I'm going to add this gain over here. And I'm going to make that gain, say 10. And now see what happens. I'll let this cool down a little bit. Then run. So now the LED is hot. Don't touch. and it's pink, which means this heater is super hot. Now LED is turned off, turn on, it will be turn off, turn on, turn off, turn on, just to maintain that set point. So online students, are you able to duplicate the results? So how do we make it better? Is this the only way to do it, or can we make it better? So clearly we can add derivative term, we can add integral term. So how do we do that? So what I'm going to do is I'm going to save this, save as test2, and I'm going to get rid of this guy, gain. I'm going to go to library. I'm going to say PID. And then what I would do is I'll grab this PID block and place it over here. So I'll grab this PID block and place it over here. And if you click onto this PID block, double click on this PID block. So there you can change the gains. So you can say the proportional gain I'm going to add to be 10. I'm going to add integrating gain maybe to 1. And I would add the derivative gain to be 0. I will say okay. And then I will say run and see if it works better. So now I think you may agree that performance is better, not the best, but better. You guys agree with me? Online students? No, I just actually, so I if you click on PID, I just put the proportional gain as 10, integral gain as 1, and derivative gain as 0. I didn't add output saturation, but you can actually, I'll tell you what happened. So stop. Just, you can actually do limit. And you can actually set up an upper and lower limit anyway. So yeah, I'll be there in just a second. Okay, with this basic, the key question remains. The key question is, how do we tune these PID gains? Clearly, you can't just keep on doing trial and error, what we are doing now. So the key question is, how do we gain or how do we control these PID gains? And for that, what I want you to do is, I'm gonna take you to this lab. So please go to AP monitor. Then go to AP monitor, take a course. Then go to MATLAB, temperature control lab. And I want you to look at this one heater lab. So the assignment for today, that will be due next Tuesday, is to do this Arduino temperature control lab. It talks about how to do this lab in PID. And do this second lab, which is for 2 PID heaters. So the assignment for today, that will be due next Tuesday, is complete this 1 heater lab and 2 heater lab and write a short report on these two labs. What? Yes, so basically if you go to this one heater lab, it will actually discuss everything, what is to be done in this lab, then how do you do this, how do you tune the PID controllers, and to tune the PID controllers, there is something called as Imc correlation. Imc correlation is the way you will find the P, I, and D control. And PID control, please understand, they will come from, remember the first lab that you did, FOPDT, the lab that you did, and you found out the time constant and the dead time. So your TC, time constant, is going to be the TP or the theta P out of these two, moderate tuning and max tuning. And basically the output of the previous lab would become the input to this lab to find out what should be the values of your PID gains. Everyone understood this? And these are the simple turn, the anti-reset wind up, derivative kick, all these things. Please read through these. And I will actually talk about the integral wind up and derivative kick when we meet in the next class, because you need to experience, you need to have some hands-on experience with tuning PIDs before I can discuss these. Everyone knows where to find these labs. So these labs, I'm gonna put this link in the chat window real quick. So this is where you will have to go and do, if you are welcome to read this section on control, but I would strongly recommend you to follow the lab that we did today and complete lab, heater lab, 1 heater control lab and 2 heater control lab. So that is going to be the assignment that is due next Tuesday. Online students, everyone okay with this? Any questions? So next Tuesday, please turn in heater 1 lab and heater 2 lab. So these two labs, and basically they are very well explained. There is actually a YouTube video on how to do it. And then basically there is write-up, a short report just like the previous lab should be submitted based on the data that you collect from your lab. Yeah, you need to include the plots as well. Questions from online students? I'm going to stop sharing. Any comment, questions from online students? And if there are no questions, I'm going to stop here and I would assign this assignment, and then please upload it onto Canvas by next Tuesday. If you are in person, I'm going to be here and I would help you with lab 1 and lab 2 just to make sure you are able to get the results. That lab should not take you more than half an hour to complete. So please turn in the lab with pictures and everything by next week, next Tuesday. I'm going to stop here and I will see you on Tuesday. Have a good weekend, everyone.